Okay, so thanks very much for the invitation. So Peter asked me to speak about this local global problem for the Apollonian packing, but to get things started, let me explain. I'm sure everybody in the room knows what the Apollonian packing is, but sort of the point of view and philosophy that we have in mind. So first of all, what do I mean by a packing? So a packing, let's say P of Rn, and I'll need a point at infinity, so is or an infinite collection, an infinite set of spheres, Sn minus 1 spheres, and we want to be able to take limits of spheres, so I'll allow planes, or planes, codimension 1 planes, so I want it to be a packing. I want disjoint interiors, so disjoint interiors. And to speak of interiors, I need oriented spheres. So tell me which way is inside. And I want them to pack all of space. So if I take the interiors, if I look at all the spheres in the packing, and I take the disjoint union, and I take the closure, so I want density. This should be all of space. Okay? So that's all that I mean by a packing. A bunch of spheres that fill up space and are disjoint. So the classic example is if you start with 3 spheres that are mutually tangent, then the theorem of Apollonius tells you how to do, with straight edge and compass, how to draw a 4th sphere that's tangent to all of them. And Arthur and I wrote a paper about how to do this very efficiently. But once you do this once, you can do this again and keep doing this forever, and you get an Apollonian. So this is why Apollonius' name is on this, although this is the only object I call an Apollonian packing. Everything else comes from somewhere else. But so the spheres all have orientations, and we'll orient these to be the usual ones, and the outermost will give the opposite orientation. And they fill up all of space, and they have disjoint interiors, so it's a packing. Okay, so this is one example. Another example is just to take any sphere and then randomly stick in a bunch of spheres and keep doing this forever. And there's no structure, and this object is not interesting to me. So we need more structure. And for that, let me say a packing. So P is crystallographic. If its limit set, so the set of limit points of all the points on all the spheres in P, is that of a hyperbolic reflection group, so geometrically finite, of a geometrically finite hyperbolic reflection group, and reflection is why I'm calling it crystallographic, acting on isometries of 1 higher dimension. Okay, so there is a hyperbolic reflection group, which is reflection through the geodesic hemisphere above this ball, above that ball, above this ball, and above that ball. So you take a point in hyperbolic 3 space, and you reflect it through this sphere, you reflect it through that sphere, and so on, and do this forever. Its limit set will be the Apollonian gasket. Okay? Any questions on the definition? So far, so good. So let me explain. So let me state the structure theorem. Structure theorem. So this is in recent joint work with Kei Nakamura. So the structure theorem of crystallographic packings says the following. If gamma tilde is a reflective, so generated by reflections, lattice, so its limit set is not something thin, its limit set is everything. So this is a lattice with generating walls, let's say C twiddle, so that these generating walls C twiddle are composed as what we call a cluster and co-cluster. With any pair of spheres in the cluster must be either disjoint or tangent, which is also the interiors are disjoint. Any pair in C is disjoint, or tangent, and any sphere in the cluster is either disjoint, tangent, or orthogonal to any sphere in the co-cluster. Any sphere in the cluster is disjoint, tangent, or orthogonal to the co-cluster. So if you have such a decomposition of the generating walls of a hyperbolic reflection lattice into this cluster-co-cluster pair, then if you take the orbit of the cluster under reflections, the group of reflections generated by the co-cluster, this is a crystallographic packing. And this is if and only if. In other words, every crystallographic packing arises as an orbit like this from a reflection lattice. Okay, so let me explain this theorem with an example. So here's an example. Let me take the quadratic form sum of 3 squares minus 1 times the sum of a fourth square. So this is the Lorentzian form of signature 3,1. The orthogonal group, the integer orthogonal group, is reflective. And you can apply, so this has a reflective subgroup. Let me call it gamma twiddle. Has a lattice. And you can run Winberg's algorithm on this. And this lattice has Coxeter group, Coxeter diagram, which is, it's even easy to write down what it is. So let's label these nodes. The nodes has 4 nodes. This means that walls 1 and 2 meet at angle pi over 3. This means that walls 2 and 3 meet at angle pi over 4, same as this, pi over 4, and all the other walls are orthogonal. So let's realize what this diagram means. Okay? So wall 4 I'll arbitrarily take to be a line. Wall 3 meets wall 4 at angle 45 degrees. So here's 90 degrees right about there. Should be 45, so this is pi over 4. Wall 1 is orthogonal to walls 3 and 4. So to be orthogonal to 3 and 4, it has to be centered at this point of tangency. So I draw an arbitrary circle. So this is wall 1, and it's orthogonal to 3 and 4. And then wall 2 will be orthogonal to 4, so it needs to hit 4 perpendicularly. It needs to hit 3 at angle pi over 4. Well, it'll do that if it's a vertical line. And so the question is, where do I put this vertical line? Well, the vertical line has to meet 1 at angle pi over 3, which means the cosine is a half, so it's exactly halfway. So this vertical line is wall 2. Okay? And reflections through these 4 walls, so by walls now I mean we're in hyperbolic 3 space. So this is a hemisphere above here. This is a wall, and these are walls. This generates, so if you were at Arthur's talk, there's a chimney, there's an igloo, and then there's a triangular chimney coming out. And that's the maximal reflective subgroup. Actually, in this case, it turns out to be the full group. Okay? Now, this diagram, this Coxeter diagram, does not have a decomposition because if I take any one wall, it always meets something at an angle that's not 0 or infinity or doesn't meet it at all. So there does not exist a decomposition for this orthogonal, for this Coxeter diagram. But we can do the following thing. If we take the reflection of wall 2 across wall 3, there is a reflective wall, so it'll still be at 45 degrees, just the other way. So this is wall 2 acted on by 3. And similarly, I can take wall 4 and reflect it across wall 3. So that'll give me a vertical line here, which is wall 4 moved by 3. And then I can forget wall 3. So I drop wall 3. And now I take these 4 reflections, these 5 reflections now. 1, 2 moved by 3, 4, and 4 moved by 3. And let's work out the Coxeter diagram. So I have 1, 2, 2 moved by 3. Okay, I don't know where I'm going to need to put things yet. So 1, at what angle does 1 meet 2? 1 meets everybody at right angles. 1 meets 4 at a right angle, except 2 and 2.3. And those it meets at the same angle as it met 2, namely pi over 3. So these are pi over 3s on both sides. Let's look at 2.3. 2.3 is tangent to 4 and orthogonal to everybody else except 1, which we already took care of. So 2.3 meets 4 at a thick line. So a thick line means pi over infinity. So the number of lines is, if they meet at angle pi over m, then you put m minus 2 lines. That's the Windberg notation for Coxeter diagrams. So these meet at angle 0 because they're tangent, so I put a thick line there. 4 is orthogonal to everybody except he's tangent to 2.3. 2.3 is orthogonal to everybody except he's meets 1 at angle pi over 3. That's what this symbol is. 1 meets 2 at angle pi over 3. 2 is orthogonal to everybody except for 4.3. And 2 is tangent to 4.3. So this is the Coxeter diagram, now of exactly the same chimney that we saw in Arthur's talk. Okay? Now we do have a decomposition. So that's C tilde. C tilde is all the walls. And C we can take as our cluster, for example, the wall 4. So this will be the cluster, and this is the co-cluster. So if we take the orbit of the wall 4 under the action of all the other walls, let's see what happens. So here's wall 4. If I take wall 4, the only thing I can move it by is 2.3. And this is exactly halfway up, so if I move it, I get exactly this line. And then the only thing I can move this line by is the wall 1. And if I move it by wall 1, well, it's a line, so it'll go through the center. So I get that circle. And then I can move that circle by wall 2, so I get this circle. And you keep moving things around, and you get exactly the classical Apollonian packing. So that's the orbit of the cluster under the action by the group generated by the co-cluster. That gives you a crystallographic packing. OK, any questions on what the Apollonian packing is from this language?
You mentioned that you're going to say that it's, well, that you want it to be the limit set of some sort of group. Can the groups be different and have the same limit set?
Yes, any normal subgroup. Any normal subgroup of this group has the same, of this group.
With finite index or infinite?
So it turns out any normal subgroup will have, OK, so there's a Thurston theory that any normal subgroup will have the same limit set, and any two groups with the same limit set are commensurate. So it turns out that the normal subgroups are all of finite index in it. But that's special about these groups with fractal limit sets. OK. One corollary, one immediate corollary, is that crystallographic packings, so crystallographic packings, do not exist in dimensions n greater than 1,000. And that's simply because hyperbolic reflection lattices do not exist in those dimensions. And this is a corollary of work of Windberg in the co-compact case and Prokhorov in general in the non-uniform ones, and these are non-uniform ones. OK. Let me just give you another example so you see this theory in action. Let me just take it straight out of Windberg's paper. So here's another example. this is with a, so it's hyperbolic 14 space, the boundary of which is real 13 space. So these are 12 spheres packing R13. And here's the Coxeter diagram. So this is the reflection subgroup of the form sum of 14 squares minus twice a square. So this is my new form. I start the same operation. Winberg computes the Coxeter diagram. Let me just draw, there are 20 walls. I'm not going to draw all of them. But it looks something like this. There are a bunch of pi over 3s. Then there's a thick line, a thick line. If two things are disjoint, for example, this wall is disjoint from this wall, so I would mark that by a dotted line. That's just that there's some distance between them. The diagram looks something like this, and then there are more things happening here. But the only thing I need you to notice is that this wall, in his numbering, it's wall 15. It doesn't matter what it is. This wall is either tangent, disjoint, or orthogonal to all of the other nodes.
Winberg is computing the reflective group.
Yes. So Winberg computes the reflective group. He gives you the reflective group by a Coxeter diagram. And so this is your cluster. Everybody else is the co-cluster. And here's a 14-dimensional, or 13 packing of 13-dimensional space by these things. Now, when you're given a diagram and you don't...
In this example, the reflective group is finite index in the automorphism of the form?
No. The automorphism, you mean OF. This OFZ is always a lattice, right?
Yeah,
So
the reflective group.
yes, exactly. The reflective group is finite index in here. Exactly, yeah. So this is reflective. It's the largest. So once you go to 15 here, it's no longer reflective with a 2. But yeah. So this is the, this is just another example to show you that this theory works in arbitrary dimension. No, I mean, when it can work in arbitrary dimension. Okay. So that's just a discussion of crystallographic packings having nothing to do with integrality. So you don't need to start with an arithmetic group. There are non-arithmetic groups, which are also, I mean, you can cook up your favorite hyperpolation group. It'll be non-arithmetic. And if it has such a decomposition, then there's a packing, a sphere packing on it. OK. But then, so there's the interest in, one of the reasons number theorists are interested in the Apollonian packing is the integral structure. So let's talk about integral structure. So let's go back to the Apollonian packing, integral Apollonian structure. So if I start with my initial 3 circles having bends 18, 23, and this bend will be negative. The outermost circle has bend negative 10. So the bend of a circle is 1 over its radius. And the sign is that the orientation has been reversed for this one. Then the next, when we do this straight edge and compass, these 7 straight edge and compass operations, the next bend will be an integer, 27. This bend is 35. And I'm sure lots of you have seen pictures of integer Apollonian circle packings. And so the question becomes, so let B of a packing be the set of bends. So in this example, it's just the set of numbers, 10, 18, 23, 27, and so on. And the question becomes, what is this set? Who are these integers? Now, it turns out, so this was observed by, so this integral structure, in the case of the Apollonian packing and one other example that I'll explain in a minute, goes back to Soddy. Somehow everybody missed this. So Descartes missed it. Leibniz missed it. But once you see that these are integers and you're a number theorist, it's an interesting question. Who are these numbers? So it's an observation in a beautiful series of papers by Graham, Lagarius, Mallows, Wilkes, and Yan, beginning, let's say, 03, that there are local obstructions. So there are some, if you take, in this example, if you take the set of bends mod 24, you'll only see the numbers, it doesn't matter what they are, but there's, you can work them out, 18 and 23. So you'll only see 1, 2, 3, 4, 5, 6, 7, 8. You only see 8 residue classes mod 24. Only a third of the numbers have a chance of even being there. And this is not hard to prove. I guess the fact that this happens in general is proved in Elena Fuchs's thesis and sort of explains all these local obstructions. And so they make a conjecture. So this is the local global conjecture for integer Apollonian packings, is that, so if we call the set of all numbers that satisfy, so A is the set of admissibles. So a number is admissible if it lies in one of these residue classes mod 24. So this is just a union of finitely many arithmetic progressions. The local global conjecture says every sufficiently large admissible integer should be in the set of bends. In other words, 24,023 will be admissible, so there should be some tiny little circle here of radius 1 over 24,023, which does actually arise in this packing. Okay, and so the very first progress on this, so let b of x be the number of elements in the bend up to x. So they proved, this is Graham, Ligarius, Mallows, Wilkes, Yan, they already proved that at least square root of the integers arise in the bend set. So this is 03. Then Peter wrote a letter to Ligarius in which he explained, I'm going to come back to this observation several times. He explained how you can actually get almost a positive proportion, x over root log x of the integers, to be in the set of bends. And then Bergan-Fuchs pushed this to a positive proportion. This is in 2011, that the set of bends is a positive proportion of the integers, so got rid of this root log x. And then Bergan and I in 2014 got the asymptotic formula. So let me write it here. It's that the ratio of the set of bends up to x to the set of admissibles up to x goes to 1. Okay, so this is an asymptotic local global theorem. So this is kind of what I want to explain how to do, and then we'll talk. So this will involve the circle method and a variety of other ideas, expansion, and things that will be relevant to the rest of the afternoon. Okay, before I do that, let me just say that this theory has been generalized to lots of other examples. So in the case of, so let me say, my student Xinjiang extended this to the same asymptotic local global, so asymptotic local global for the packing where if instead of just placing a single circle in every interstice, there's actually a conformally rigid way of placing 3 pairwise tangent circles. Well, that's why I usually let the computer draw circles for me. But there's a conformally rigid way of placing 3 in here. And so this is what we call the packing modeled on the octahedron. It appears already in a paper of Boyd's from 74. So this, again, has an integer structure. And you can ask the same integer local global question. And this was proved by the same asymptotic local global statement was proved by Zhang. And most recently, Fuchs, Stange, and Zhang kind of extended this theory to the greatest, in the case of circle packings, the most general case it should be, which is, so asymptotic local global. I'll explain what this is, assuming the packing, how do I want to say this? Assuming there is a congruence stabilizer. Congruence, and I'll explain what this means. Congruence stabilizer. Okay, so I have to explain what this means. And it comes, what it means comes from this observation of Sarnak's. But before I do that, let me just point out a couple more things. Okay, so is the statement of this theorem clear? This asymptotic local global? And that you can do it for various other examples. Let me point out, so this is, again, in this work with Nakamura. So this condition, this congruent stabilizer condition, will hold for infinitely many conformally inequivalent integer crystallographic circle packings. And it will also not hold for infinitely many of them. So it works infinite often, and this condition, this technique does not work infinitely often. So the first thing I should say is there do exist infinitely many crystallographic integral packings. So this, people had constructed various, finitely many examples of such things with various increasing levels of complexity, but there's no hope of saying, well, this is all of the objects, because you can construct infinitely many in very wild ways. On the other hand, we do show, okay, so I don't really want to go into this theory of the superintegral ones. Let me just state a theorem. So this is part one. Part two is not just integral packings, but superintegral packings. So there are only finitely many superintegral. I'll explain what this means in a second. Superintegral such packings up to commensurability. Okay, so I have to explain a couple of things. First of all, what I mean up to commensurability, so we'll say that two packings are commensurate if they're these supergroups gamma tilde that come from the structure theorem are commensurate. And then what we really prove is that if a crystallographic packing is superintegral, then this supergroup is actually an arithmetic reflection group. And there are only finitely many arithmetic reflection groups due to Agel, Belopetsky, Nikulin, Reed, McLachlan, a lot of names in that direction. Winberg, of course. Winberg, so I already used Winberg here. So, but yes, Winberg is everywhere. Winberg is everywhere in this theory, absolutely. So I didn't say what superintegral is. So a packing is integral. Oh, maybe I didn't define it. A packing is integral if every bend in the packing is an integer. And what is the packing? It's the orbit of the cluster just under the co-cluster. But if you take the orbit of the cluster under the full group gamma twiddle, you will have many more spheres. So you're allowing reflections through the spheres themselves. So this sphere reflects into here and so on. So there's a big mess of circles. And it might turn out that all of those simultaneously all have integer bend. That's what superintegral is. So superintegral is not only is the packing itself integral, but the orbit of the cluster under the, not just the thin group, but by the thick group, by the lattice, all has integer curvatures, integer bends. Okay? We also show that there exist packings that are integral but not superintegral. So these must come from non-arithmetic groups. So this whole theory, if you weren't here for my members seminar in September, you can see it on YouTube. I'm not going to go into it again. But the point is there are infinitely many crystallographic packings, and there's some classification, up to this notion of commensurability. And then part 3 is what I just said. Let me write it down. For infinitely many, this congruence stabilizer condition holds. Congruence stabilizer is true. And for infinitely many, it's also false. Okay, so this general asymptotic local global problem is far from resolved. It's been generalized as far as it can be, and it handles lots of cases, and it doesn't handle lots of cases.
What are you saying is false?
So I haven't explained what the congruent stabilizer condition is, so I'm going to do that right now. No, not the local global. For infinitely many such, the congruent stabilizer condition fails. So let me explain what the congruent stabilizer condition is. Oh, let me say one more thing before I go into that. What about higher dimensions? Let me just say this in words. In higher dimensions, so Soddy had already considered the case of sphere packing. Let me draw the planar picture, the strip sphere packing. So if I take a plane on top and bottom, and three mutually tangent spheres, there's a plane on top and a plane on bottom, there's a conformally rigid way to put more spheres in. And you continue this Apollonian picture. And again, you have this integrality. This was all observed by Soddy. And in this case, I was able to prove the full local to global theorem using this congruent stabilizer. The congruent stabilizer condition gives you much more in this dimension. OK, so let me try to explain what the congruent stabilizer condition is. And it comes from this observation. So it's the following. Any questions so far on the statements of these? So there are infinitely many of these crystallographic packings, but only finitely many up to this notion of commensurability if you have a stronger condition, not just integrality, but superintegrality. Let me explain what this congruent stabilizer condition is. So if you want to prove this local global theorem, or this asymptotic local global theorem, it's enough to do it. I mean, this is taking the orbit of potentially a whole bunch of spheres. By the way, in this picture, I could also have taken these two spheres, these two walls to be in the cluster, because these two walls are themselves disjoint, and any edge leaving this subgraph is either a thick edge or no edge or a dotted edge. So they're either disjoint. I'm just saying that this condition is satisfied. They're either disjoint, tangent, or orthogonal to everything else. So you don't have to take a single sphere. You can take lots of spheres in your cluster to take the orbit. But to study this local global problem, it's of course enough to do it to look one orbit at a time. So let's fix some sphere in the cluster, and let's look at the orbit of that sphere under gamma. Gamma is the group generated by the co-cluster. So it's this thin subgroup whose limit set is the same as the limit set of the packing. OK. Here's the condition. So this orbit, so definition, this orbit OS has the congruence subgroup property, congruent stabilizer property, not the congruent subgroup property. That's something else. Stabilizer property if. So there needs to exist a sphere S prime, which is tangent to S, so that the stabilizer of S prime in gamma, so this is the stabilizer in gamma of S prime. This will be a lattice, it's not hard to see, in one lower dimension. So this will be a Fuchsian group. This is congruence. Let's look back at the Apollonian packing. So here's the Apollonian packing. The group generated, or A group, since there are any normal subgroup, A group generating the Apollonian packing is the one generated by these reflections that we drew before. 1, 2, 3, 4. And I can take the cluster, if I want, I can take the cluster to be the 4 white circles. So let me take a single circle. Let's say I'll take the orbit of this circle. So this is my circle S. And if I look at a circle tangent to it, so here's my circle S prime. What is the stabilizer of S prime in gamma? Well, it's the group generated by these 3 reflections. And in fact, this is a fundamental domain for that action if I treat the S prime as the boundary of hyperbolic space on which that acts. And this is commensurate to gamma of 2, the congruence group, the classical congruence group of index 2. Okay? So there's a sphere or circle or tangent to S. There's a circle S prime which is tangent to S, so that the stabilizer in gamma of S prime is a congruence group. And Sarnak's observation is if that happens, then the set of bends will contain values of a binary quadratic form. And binary quadratic forms represent at least x over root log x numbers up to x. Okay? So that's where that paper, what's done in this letter. Then if you combine a bunch of these binary quadratic forms in a very clever way, you can get rid of this root log x. So this is using quadratic forms. But it's very hard to tell which numbers you're getting in this method. And this method is using the circle method. This is what I want to try to explain in the remaining 6 minutes. So this is the circle method. So the circle method will use all the tools that we're going to hear about the rest of the day: expansion and Diophantine analysis and so on. Any questions so far before I go into what the circle method is doing and how it works and so on? Is this clear? Okay. Well, so how are we going to capture bends in this orbit? So let's pick a parameter x and let r sub x of s of an integer n be the sum over this group gamma. Let's take your favorite Archimedean norm and fix a ball of size x in that Archimedean norm. So just cut it's an infinite group. I want to cut it off to have things of size x. And then I'll take the indicator function that n is equal to the bend. So if I take gamma in here, the bend of gamma s. So what is this saying? Take your circle S, move it somewhere. Here's gamma s. Gamma is some element of the group, so it moved it around a whole bunch of times. You got a new circle. What was its bend? If its bend was n, then I contribute 1 to this sum. Okay, so this is the multiplicity of the integer n in the set of bends among these elements. Okay? And the stupid observation is if this number is not 0, then arise in the bend set, obviously. Okay, so as usual, we're going to recover this as an integral. As usual in the circle method, we'll recover this as an integral over its Fourier transform. What is the Fourier transform? The Fourier transform is just the same sum where this is replaced by the exponential sum e to the 2 pi I n times the bend. So this is Rn. This is the representation number. And the way we evaluate this is to break it into major arcs, and minor arcs. So let's call this the main term plus an error term. So far, I haven't done anything. What are major and minor arcs? So any theta, you can write, there's some choice of parameters. You can write any number in 0, 1 as being some rational number plus some error. Well, this is completely vacuous, but there is a way of making this precise. Those that know, know. And the major arcs are the ones where the denominators are small and the error is small. And what is meant by small is a technical condition that, again, if you know what it is, you know what it is. And if you don't, then me telling you won't help. But it's some very tiny bit of the full interval. And what you can prove, so using expansion, so super approximation, or Ramanujan, or expansion, expander graphs, all kinds of ways of saying this. In the case of the Apollonian case, I should point out, using super approximation for all Q, not just square free. So the people that work on this expansion problem are very sensitive to the fact that the general setting we only can do for square free numbers, which is enough for sieving purposes. But for circle method purposes, we need all numbers. In the case of the Apollonian packing, this super approximation is proved by Varyu. And in this completely general setting, there's now a paper that can give a version of this by Zhang and Salehi Golsafidi. Zhang. Okay, so we do have this for all Q super approximation statement. Let me not say exactly how this works. What you prove is that the major arcs do what they're supposed to. So the main term is at least of size. Well, so how many points were there here? It's just number of elements in a ball, which is x to some Hausdorff dimension, divided by x, because the bends will be of size x. And then there's some singular series. And the singular series vanishes if n is non-admissible. Okay, so this is really how the completely standard process for how the circle method works. And if you could prove that this error term is little o of this main term, then you would prove the full local, not the asymptotic local goal, but the full conjecture, which is still wide open. And we have reason to believe that at least these methods will not be able to prove that theorem, because we can construct a very similar situation where you have an orbit of a group, and the local global principle fails in the sense that a number passes all local obstructions, but for group theoretic reasons. Okay, so I mumbled that this is of size, that the number of elements in the ball is x to the delta, where delta is the Hausdorff dimension of this packing. And if you divide by x, you're subtracting 1. So, and then this is like log. So this is x to the little o1. The point is delta is bigger than 1, because at least circles are in the limit set. So this exponent is positive. And if this exponent is positive and x is big enough, well, this number must be at least 1, at least 0. And if it's a representation of it's an integer, it's at least 1.
So you're hitting it. The reason this problem can succumb to the circle.
Yes.
You're hitting it very often. You're not only expecting that n is hit, but it's hit
yeah,
power.
And to a power, a small power,
Yeah, yeah.
but it's a power. It's positive entropy, absolutely. Yes, lots of multiplicity. It must be multiplicity.
So that's why you have a chance to do it by analysis.
Yeah, otherwise.
No, you're going to see. No, in the next lecture, this will be down to 0.
Yes, exactly. Yeah. So what if the number of terms is logarithmic, then you're in big trouble. So no, we have positive entropy here. Anyway, I'm basically out of time. Let me just say that we do not know how to handle the error term. So we can't prove the full theorem. What we really do is we handle the error term in L2, and if you handle it in L2, you get the asymptotic local global theorem. Actually, I lied to you completely. We don't know how to handle this error term as it stands. What you have to do is break up gamma. You reintroduce a new sum. You change the problem slightly. You take this congruence subgroup in some ball, and you take gamma in sub ball, and you create bilinear forms. So this is gamma prime in here. You create a bilinear form structure, and if you remember what I mumbled before, was that this set is capturing binary quadratic forms. So now you're capturing, now you have arithmetic tools to try to get an L2 bound on the error term, and that gives you a power savings on the exceptional set. Okay, let me stop there.